So far in our all the past sessions, we were using simple RNN, and then we wanted to reach out to attention, which is our main motto for moving towards the large language model, to get a good understanding of attention. So having achieved that in the last video, why we are coming to LSTM? The reason is that in the literature, whenever you see that they are speaking about RNN, essentially it is LSTM. RNN for its vanishing gradient problem, which we discussed in our second video. It's not good for learning sequential tasks. So LSTM was the breakthrough, where the gradient vanishing problem was largely arrested through gating mechanism, and therefore if we don't cover the LSTM, then we'll leave a large void in our learning. When you see in the literature, we'll see most of the implementation of attention in the pre-transformer era has happened with the help of LSTM or one of its variants. Let us now jump into the concept of LSTM. How does it work? You will remember this diagram where these RNNs were unfolded along the time axis. This is one of the cells of the RNN. This is one of the neural network layer, which you can call it as a cell of RNN cell, which has got two input. One is the word vector itself, and second is the hidden state from the previous time state, and then it was giving you one output, which is the hidden output only. So this entire block of light blue color, we can call it as a RNN cell. Now let's move to the LSTM era. So you can think of this that blue small rectangle is now expanded as this light green color rectangle. Next thing we are going to do is map our word vector as the input, as it is coming in the previous RNN, simple RNN as well, and the hidden state which are coming. They are concatenated. They are joined together, they are concatenated and created a single vector, concatenated vector. Next, it is passed into a neural network, which we call it as the output weight. Then finally it is activated by sigmoid activation. So the output will be definitely activation of W0, the weight, and the vector, which is concatenated vector of ht minus 1 and xt, right? And some biases. So that's the standard neural network formula. And that is what we are calling it as the output at time step t. We started with t minus 1. So now the t output has given. And then it is expected to give that hidden state ht, right? But yeah, wait, this is where LSTM will change. It is not immediately giving the output, but it is also taking one more input, which we call it as a cell state input. This is called a C, denoted as C, is called cell state. Whatever cell state has come, that need to be controlled in terms of how much it will be remembered and how much it will be forgotten. So that is where the LSTM is often called a gating mechanism. So the first gate is coming into picture, and to create the gate, they are passing it through, they are taking the same input of concatenated vector, this ht minus 1 and xt. That vector is passed through another weight, which is called the WF, forget gate weight. So this is output gate weight. Now it is passing through another layer of weight, a neural network, and then activation is done on that, which is acting as a controller. Why it is so? Because sigmoid will output something which is within 0 and 1 range, right? That output is multiplied with the cell state. It basically weights each of this value of cell state, right? It will do a weighting, and therefore the matrix multiplication output will be nothing but this forget gate value multiplied by the cell state. So the cell state is controlled by forget gate. Now this is about a gate creation for the previous cell state. Now what about the current cell state? To create the current cell state, we will again take this input. So you see how many times we are using the same input, concatenated vector. 1 here, right? Second is here, and third is here. So the third input will go and again go through a tanh activation. Tanh, the nature of tanh function is that it will give you output within the range of -1 to +1. So some regulation, it will not go wide any values, but it will stay within -1 to +1. And all this tanh, because of this range regulation, will help in preventing the gradient calculation as well. Like the previous cell state was controlled through a forget gate mechanism, we are now controlling the current cell state using one more controlling gate. So this will create the cell state and this will control the cell state. So this is the fourth time the input is again used, and this time it will be again passed through a sigmoid layer. like we said that the sigmoid will give output value within the range of 0 and 1, but the cell state will be within the range of -1 to 1. So this will be a created value. This will be controller value because it is within the range of 0 and 1. It will act as a weight. These two will be multiplied. Very similar to what forget gate was doing. The FT was used as a weight for the cell state CT minus 1. So here IT, the input gate they call it sometime, will act as a weight for the C dash T, which is the current cell state. Okay, together they will form the output, which is kind of is an update gate. We can think about this as the updated value of the current cells. So now we have the current cell state value and the previous cell state value controlled by some gating mechanism. The final cell state will be given as the output CT. So CT is nothing but a summation of, look at this formula, is the previous cell state controlled by FT plus the current cell state, which is C prime T, multiplied by IT, which is input gate. We can now think that how the CT minus 1 was formed in the previous step. It was the similar process which followed the previous state as well. Fair enough. So we had the CT as the output, but where is HT? We had given HT minus 1. We are yet to get the HT from this output, right? So how HT is given is you take this final output of CT, pass it through a tanh layer again, and then multiply them. So this acts as the final weight for HT. This is the out. So every HT has a component of CT. So when you do the derivation, if you remember dou HT by dou HT minus 1, it was leading to only one weight, but now it has got a component of CT. The derivation result will be different. It will be additive in nature. You can see there are three gates we have displayed here. One is the forget gate to control the previous cell state. One is the input gate, which is to control the current cell state, this block, green block, and one is the output gate, which is the output as is going through, but CT is controlling here. So three inputs given, two outputs are expected from the LSTM cell. Now, as you can see from this line, this yellow color line, the cell state is passing through the network with some gating mechanism, but it is able to carry through the information from time step to time step. And that acts like a conveyor belt. That's why it is called a constant error carousel. So this allows the information to flow without any barrier from time step to time step till the end of the time step. We get some intuition. Cell state is helping the LSTM to maintain the information along the timeline, which was not there in earlier simple RNN, is one clue we are getting why this can be used as a remedy for the vanishing gradient problem. But if we have to go a little bit deeper, then we can see that what exactly was causing RNN to get into this vanishing gradient problem or exploding gradient problem was this term, which is when we are trying to calculate the loss with respect to HT minus 1, then we were getting this term, which was dou HT and dou H with respect to dou HT minus 1, which was resulting into the recurrent weight WR. Okay, now this WR was finally was summed up for all time step, then it was raised to the power T minus 1, and that was actually when this the eigenvalues for this matrix were less than 1, it was causing the gradient to vanish. In contrast, when you are coming to LSTM, we have this term CT minus 1. So following the similar analogy, somewhere we'll get this term when we are doing the gradient calculation, derivation, we'll get this term which is dou CT with respect to dou CT minus 1, right? Because LSTM will also give, along with HT, it will give the CT also as the out. This term, when it is the derivation is done, you can see will result to FT. Okay, the forget gate output will be the output for this, because this will cancel, plus some additive term will come. You see this is coming very similar to what was coming as the recurrent weight, and then
dou L by dou HT. So here we see dou L by dou CT, but instead of recurring weight, what we are getting is the forget get weight. Therefore, if the forget get weight is learned properly, we can ensure that it is never going less than 1. Okay, it can be 10 to, it will never go very small. If the learning is proper, then it will send a feedback to the network that you don't forget much. And that's how this will help you to retain the information. Also, there is an additive term when you do expand this calculation. Unlike the nature of the simple RNN was multiplicative, but here it is additive. This additive nature of gradient also help arrest the vanishing gradient problem. That's what we had written here as green color. The nature of derivation changes because of this CT. The other thing we are implementing here is, which is bidirectional. So the first thing to note is that in the LSTM network, like we displayed or discussed in the expanded cell architecture, we can now consider these are our cell for each time step, and each time step now is not only giving HT but also giving CT as the output. So that is one pattern which will follow going forward in our code and in the subsequent slide also. Next thing, we have also added bidirectional RNN. Earlier the words were getting fed from x1 to xt. Now we will also do the reverse, which is along with this it is going to feed xt to x1 in the reverse direction. So one is going from bottom to top, and then one more RNN, bidirectional RNN, would mean that this should also read from the top to bottom, xt to x1. Therefore, each of this input is getting doubled up. Now it is learning the context from both direction, and it is doubled up, and therefore each of this value, output value, will also get doubled up, which means that HT will be HT right and then HT left. Similarly, the CT will also have CT right and CT left. Each of this vector will have 2, and there will be two direction of learning, and then it will output the concatenation of left and right vector. And similarly for all time step this will follow. So essentially we are talking about the vector to double up when we use bidirectional RNN. Because this is doubled up, the context vector what will be formed here will also shape a different dimension, because this is again getting doubled up here. Fair enough. With this, now we can go to the code. In the code, the first thing to be noted here is that what changes we are making. One changes we'll do is the data adjustment. So, but before going to data adjustment, let's see what was the data before. You see, the data used before as tokenization and vectorization, the data was converted to 1 hot. The data preparation or the data preprocessing steps were like this, that we do the tokenization, which can be of various format. It can take each character as a token, or it can use spatial delimiter to split the sentence into smaller chunks. But at minimum, we can use the spaces in between the sentence, and each word can be considered as a token. Many times this to and all those prepositions are stripped off, and only the useful words are retained. From this word, now we are going to convert this as a number, text to number. Basically, if this is a 4000 word vocabulary, the total number of words which are used in the entire corpus, we are speaking about all the sentences using which we train the model, that's what is called the corpus. So then we can think of a large array of 4000 indexes, and each word is now assigned with one index, right? So therefore, assuming Tom was at the 80th index, Tom's text to number value will be 80. And similarly, the reverse can be done by using this indexing as well. Now the choice comes that how do we give this number to the model? We don't give this number directly to the model RNN. So one of the method has to be taken. For example, we can convert this as 1 hot, which we were doing so far, because it is very easy to understand what we are doing here. Basically, that is again array where all the indexes are 0, as you can see here, but only the 80th index for Tom is given as 1.
and that is very inefficient in terms of when the output of the data comes, it requires huge amount of memory. You can imagine the amount of memory it will require. Also, lot of data going to model, so model will have to learn that much of 1 and 0. One we are now using is word embedding. Up to this part is same. What we are going to change is this number is now going to go to another neural network, which is called a word embedding model. By the way, this is about word vectorization, and there could be different techniques which we can deploy to convert a word as a vector. There are specialized model available for this. Very popular model is word2vec, globe, etc. But they are all pre-trained model. When we use word embedding, we are deploying a neural network within our RNN model itself, which will learn the appropriate word representation based on our own corpus. So it has got some advantage. Well, now word embedding is the input is the vector size, which is 4000. Output is embedding size, which is a hyperparameter, which we decide. Thereby, the embedding dimension can be less than the vocabulary dimension. Now it is fed into RNN. You can see that earlier we were doing this using the one hot encoding, and they were like this, and therefore our outputs were all like we said that it can be 4000. So it is 4680. Each word was that much of dimension. The decoder input and port were even higher, 7429. Hard for us. Fortunately, I have a lot of memory in my personal computer, so I could handle this and show this to you. But when I wanted to implement this in, let's say, Colab, my Colab crashed. It could not. Even with paid Colab, I had struggled by doing this. Now we are changing this to don't convert it to one hot encode. Just after padding, I am returning those output without one hot encoding. Then this data after the adjustment is fed into the encoder as embedding layer. And if you look at my variables this time, the embedding dimension is 256. So what was 7229 is now become 256 dimension of vector. You can understand the efficiency we are introducing by incorporating an embedding layer. It is not only a pure vanilla conversion of word to vector, but it is also learning context. It is actually learning what was the previous word, what is the next word. So embedding is very powerful that way. We are now, instead of simple RNN, we are introducing LSTM. So in Keras, this is how you just call the LSTM layer, and every other stuff remains same, which is return sequence and return state is very similar to what we have done in simple RNN. We spoke about the bidirectional layer, which is to take the input twice, one from top to bottom, one is bottom to top, or sometimes we tell it as the backward and forward. So this is the bidirectional layer which does this job. So LSTM is supposed to give you two output, right? One is all the output because it is true sequence is there. That is one output which you are anyway getting. And then you are going to get the hidden state output. Very similar to simple RNN as well. These two we were getting previously also. But because of LSTM, we are now going to get the C state. You see the C state is coming, cell state. So this is 3, which you will normally get. But because it is bidirectional, we will have a forward edge corresponding to backward edge, and then forward cell state. So you will have a backward cell state as well. And then this forward cell state and backward cell state will be concatenated here. This is the cell state and this is the hidden state, who are actually concatenated. And because of this concatenation, your states are basically doubled up, which means that if we have in our variable RNN units, so at 256, we are now going to get 256 into 2 as the output because of this concatenation which is happening. Let's check it here. You see, this is the all time step which is coming from return sequences. If any of you is getting confused what I am meaning by all output and single output, you have to go back to my first video, which is the RNN basic. So now you can see that this is the all time step, which is 6 number. There are 6 words, and the dimension of each word is no more 256, but they have doubled up to 512 because of the bidirectional concatenation. And the hidden state also, hidden state and the cell state also is the same dimension, 512 each. So that's about the encoder implementation. Similarly, the decoder implementation also follows embedding layer. Everything remains same, but one thing need to be changed because the dimension has changed from RNN units, which is 256 here, to 512. The decoder also need to have RNN units multiplied by 2. So that's one change you do. Similar to your LSTM, because we are using LSTM as the decoder as well, we can expect that there is a cell state which we will also get from here. Decoder output, decoder state H, decoder state, this should be C. I have not used it properly. Typo here. So this will give you the cell state H, and this is going to give you the cell state C. And then the initial state is the encoder states, which is basically 2 now, state H and state C. And then sequential model, everything remains same. We are going to this is just for the testing. Okay, this is the second part of the code changes. Third changes we are going to now talk about is the attention layer. Our intention is to also capture the attention weights and then finally utilize them for visualization purpose. So in order to do that, we modify the attention class as well. Two changes we are doing. One is we are introducing a name because we have to identify the attention layer name for the encoder and the decoder separately. Okay, so we are making this change here, which you can note how it is done. Okay, and second change we are introducing in the output, we are also returning the attention weight. Earlier we are getting only the context vector. Now we are going to get the attention weights as well. This is the third change which is incorporated. Here is what we are trying to build the exact model, LSTM combined with attention. Almost everything is same as with respect to our previous video where we had done the similar thing using simple RNN and unidirection. You can pause this video and look at it in detail and you see that there is nothing much has changed. Only thing to note that each one of them we are now giving a name to distinctly identify what is doing what purpose, which we are going to utilize later. I'll show you later. So give this name. This name becomes important here to identify. Okay, you iterate through this and we just want to reiterate and note it once again how the attention layer is called here. Attention layer is called within the loop and here is the attention and we are calling the decoder attention train here with the state and the encoder output. However, now we are also receiving one attention weight here. This attention weight, we are collecting it in one array. This is the array where we will collect all the attention weights. This attention train will be converted as a tensor and then finally appended there. Attention weight will look like this, right? 161. We want to get rid of this 1 and that's what we are doing here as a squeeze operation. TF squeeze attention train. Now we started training the model, but the training actually we did it in my previous version. So I'll just go switch there and just show you. We trained it for 10 epochs with some additional stuff, which is checkpoint and early stopping. This checkpoint will help me save the model as it improves the accuracy. Okay, after training this an additional 10 number of steps, I could achieve 96.46% of accuracy and I created a version 5 of this notebook and in that I am not going to train but I am going to load the weights from my previously trained model which was the 96 accuracy. So now interesting part comes that I want to visualize the attention. So how do I visualize this attention? Is this attention weight going to help me? There is a problem here. Look at this. When I am building this training model, my output is decoder output TF train. One output is expected, which is the output vector itself, which will be compared with the level, and that's how the loss will be calculated. So for the model to work, the loss calculation can happen only when there is one output without subclassing the layers. I am using the API layer, right? I am using the functional layer. So without doing any customization, it will definitely expect the model is giving only one output. So how then we are going to use the same model where I also need the attention weights as the output. I cannot do that. So here is a trick now. What we are going to do is build another model to get the attention out. At this stage we are using the model, but instead of giving output of only the final decoder output, we are also taking the attention weight as the output. So the model has changed, but all the layers which were there were the same. That's how you don't have to retrain. But additionally, optionally actually, we can set this weight. We can take the weight from the training model. Our training model was this one. So I can take the weights from there and then set it here. Set the weight to this model. Because the only thing which is changing for this model is the output. All other things remain same. I am building a function here which does the conversion of sequence to word. Given a number, we want to get the word. We are going to do the plotting function. So the plotting function is very easy. You take the attention weight, you take the source language which is English, and you take the final prediction which will come out from the training model, and that's it. Then you plot them. You plot them here in sns.heatmap as attention weight, which is this weight. Okay, convert it to a numpy in case this is a tensor, and then in the x-tick level horizontal axis you show the source language words, and in the y axis you just show the target language words, and then call the model, training model here we're just calling. These are all helper printout to understand what is the source and what is the target actually. Then this line is where we are calling the training model to predict. This is the only line which is doing some new job here. So it, as we expect that it will do prediction, and also it will get the output weight from the attention weight from the prediction. You are giving the lang1 sample and lang2 sample. Randomly you are creating one index and giving it here, and then use that language sample as the source and target, and therefore you are getting the output. And note here that even in this training model we are forced to give both, because the model architecture was such. So it is still not very real, but just to give you a feel that how model architecture can be changed to change the shape of input and output. Okay, so once we do that, we have the attention weight collected, and the same attention weight and this prediction language we are going to give it to the plot attention function which we had done before, and the plot will start generating. Coming to the plot generation, and you see some of the plots got generated, and I pick up some random index from my training data. It is going to give you a plot. Here you have some English sentence, and here you have the words in the scale shows that wherever it is very dark, that is less score. Wherever the color intensity is low, this lighter color is basically higher weight. So you see Tom, when it was given Tom, the model focused the Tom, very nicely identified. Rest of them, maybe it's not a one-to-one translation, so it is struggling. For example, is it notch, maybe I'm just thinking that these two words maybe isn't one word here. So it has struggled a bit, and when we reached up to up, it has again matched something here up with notch, and when it is coming to yet, then possibly this should have come here, the red color, but it is one step before it has given the attention. But you can see as the words are moving forward, the attention is also changing, and somehow attention has really played a very good role. Let's see some more example. Yeah, this here also you can see there are three words. Here it is something like I will or I. Here it is each, so it is focused properly. When it moves further, forgive noun, so it says that because it is less word, one particular word has focused in many places, but at the same time Tom and Tom is the highest. So when it is a one-to-one correspondence, the attention has really worked very well. So here and here. I must say that this attention, when I tried to implement with the simple RNN, it was horrible. It was not that good. That's why also I had improved it to LSTM bidirectional, increase the context vector length so that it captures more information. But there are several other hyperparameters, for example the embedding dimension, the number of layers which I'm introducing, all those can be changed to make it a very perfect attention graph. But what it explains in a complex situation, you must appreciate that when you are saying I will, what caused model to predict which word is getting now visualized. So attention visualization is a step towards understanding the model's behavior, or a step towards explainable AI. So suppose this is kind of predicting a disease or used for medical cases, attention plotting will help to identify that given this pathology reports, and if the prediction is fever, what exactly, which report of the prediction or pathology has caused model to predict that this is a fever. Well, I have several other plots, and some of the places attention really had worked well. But as I'm saying that this is, you shouldn't take this as a kind of a ready code which can be deployed in production. Definitely not. There will be more fine tuning. You will not build your own custom layer of attention. Attention layers are already there in TensorFlow, so that can be used, or PyTorch. So they are much more advanced, fine tuned. Okay. But this is, we are doing it by hand, one step at a time, and keeping it very simple so that we can develop the intuition and the mathematical foundation without any additional complexities of code. So to summarize in this video, it was a long video. We learned several things. At first, we understood the importance of LSTM, then learned how internally LSTM LSTM implements the gating mechanism, where it incorporates one additional state, cell state, which retains information across longer time steps. And the cell state, previous cell step, the present cell step, and the output are controlled through three different gating mechanisms. One is forget gate, one is the input or update gate, another is the output gate. Gating mechanism is nothing but calculating a weight which will be multiplied with the actual signal to say how much of it to retain and how much of it to forget. Now subsequently we understood that having that additional cell state CT has the impact on the gradient calculation in terms of adding some additive term. So the gradient never vanishes as fast as what simple RNN could do. Then we re-implemented our entire code using LSTM, and we noted that the outputs are also coming up with the CT is coming up. We implemented a bidirectional RNN which allowed us to get the context information of the input from both direction, forward direction and the backward direction, and therefore each of the output actually doubles up. So it contains more information from bidirectional perspective. So together with bidirectional RNN and the LSTM, we got a higher dimensional vector as output from 256 to 512 from the LSTM encoder. Next, we modified the LSTM model to output the attention as well, and then visualize those attention, and we understood how the trick played in terms of using the same layer from a previously trained model, but doing a bit of architectural change in terms of input, output and the connection probably, but the training and the weights can be still reutilized because we have not changed the architecture. So this is a fantastic trick which can be implemented when you are doing research or trying to develop new architecture of models.